for 284C3M1B7C8E13C9C6D3P38D19D7b44. Slide 22f1fa19c3m1b7c8e13c9c6d3p38d19d7b44. Kerr Combs Ytterbium doped fiber signals 5G Wow Seti. See, there's the fiber was spelled with B-E-R and the other one's B-R-E, so that's what was the confusion. There's the alien radio signal there. This is the data from May the 4th, 2013. So we're talking about pump laser fiber signals, Kerr combs for UFO communications from outer space in the WOW data, keyword PDF results, and keyword research. So we started at line 37 for this particular line, and we're up to 44 now. So mid-infrared optical frequency combs, then we did CW mid-infrared OPO pump laser, then we did a high power comb line, then we looked at phase noise infrared signals and infrared comb nodes, frequency signals and frequency comb spectrum signals, then telecom wavelength semiconductor signals. Keywords were Fonula particles, wavelength formulas, and Compton wavelength. From Fonula units, tile mole, and 1472, that's where the PDF results came from. So I'm quote from a blog. This was the original scientist that worked on this PDF file. From Nature Communications, January 2013, material choice. The suitable platform for mid-infrared Kerr comb generation should possess the following properties simultaneously. Wide transparency window in the mid-infrared, low loss for achieving high Q cavity, Kerr non-linearity N2 anomalous GBD, the same size of thermal coefficient of refractive index dN, dt, and thermal expansion coefficient A. The last criterion comes from the thermal instability described in the supplementary notes section, which has a key role for stable operation for Kerr combs. In supplementary table S1, we list the dielectric crystal materials under consideration with their respective properties. All the materials have positive thermal expansion coefficients. As can be seen from supplementary table S1, although most of the fluoride crystals have wide transparency window in the mid-infrared and almost GBD, they have negative dN dt, which would induce thermal instability and render thermal self-locking inapplicable. Silicon nitride has a normal bulk GBD in the mid-infrared, and the current fabrication difficulty to grow Si3N4 waveguides thicker than squiggly line 800 nm makes mode confinement and dispersion engineering very challenging. Interesting. The reason I'm going is because there was a section in line 22 that talks about growing crystal wafers. Yeah. It's got PDF results for it, so I guess we'll have to cross-reference that and see what it says, right? The two suitable materials for mid-infrared Kerr comb generation from the list would be MGF2 and AL203. In this work we choose MGF2 because fluoride crystals such as CaF2 and MGF2 have lower material absorption, therefore could reach higher Q than AL203, especially for wavelength longer than 2 ohm, refer to 40. In addition to dielectric crystals, many semiconductor materials also possess wide transparency windows in the mid-infrared and strong Kerr non-linearity. Non-linearity is a huge word that keeps coming up in with this communications device. So I still don't really understand what it means, but obviously it's important because it comes up a lot. The advantages of semiconductors are that they allow on-chip integration and are more versatile for waveguide dispersion engineering. Supplementary table S2 lists several possible semiconductor materials for mid-infrared Kerr comb generation. This is going to include silicon, which there is a formula that came up with silicon already with crystals, and I obviously have to cross-reference this in the future. Si, germanium, Ge, aluminum nitride, AIN, gallium arsenide, that came up to GaAs. There's a whole formula with the GaAs. There's a formula with that. And indium phosphide, IMP. The unwanted 2-photon absorption is avoided once the photon energy, see, we're talking about photon energy again, is less than half the band gap. For example, waveform is greater than 2.2 for silicon. Therefore, the material loss is lower in the mid-infrared. I'm assuming that's the waveform symbol. It's the upside down Y thing. While we do not find the experimental data on the bulk Kerr nonlinear tree 2 in the mid-infrared for AIN or ALN, GaAs, and INP, it is expected to vary as Eg to the power of -4, where Eg is the band gap of the material. Although Si and Ge have normal bulk material, GBD, in the mid-infrared, it is possible to create a spectral window of anomalous GBD by carefully designing the wavelength geometry. For example, for an Si ring resonator of radius 50 with 900 nm and height 400 nm, it is expected that GBD would be anomalous between 2.0 and 3.2 Set up for microresonator-based mid-infrared frequency combs, the employed pump laser is the idler beam of a high-power single-frequency CW optical parametric oscillator OPO Aculite Argos model 2400. The pump of the OPO is a 15W Ytterbium doped fiber-based source operating at 1064 nm, and the OPO is a 4-mirror ring resonant cavity using a temperature-controlled MgO ppLN crystal as the nonlinear element. Now, see, it says 4-mirror ring. Isn't that interesting? And then in the design, we have mirrors set up in a ring formation to diffract the laser beams. So that's cool. The idler beam is tunable from 2.4 to 3.2 with up to 3W output power, corresponding to a signal beam from 1.9 to 1.6 The idler beam can be fine-tuned by piezoelectric tuning. Again, piezoelectric is another keyword that has formulas. Tuning of the pump fiber laser. Fiber pumps, lasers, that also has formulas in the line of data as well. Both the idler and the signal beams have a specific line width of less than 1 MHz. The tapered fiber waveguide is made of low OH fused silica fiber, which is single mode at 2.5 The idler beam of the OPO was coupled into the tapered fiber by an AR-coated spherical ZN-SE lens. A coupling efficiency of more than 60% was obtained. The optical spectra of the combs were recorded by Yokowaga long-range OSA. A second OPO similar to the pump laser source is used as the narrow line width CW laser in the beat note measurement. The beat notes are recorded using an extended in-gas detector with 100 MHz bandwidth. How to cite this article? Wang, C.Y. et al. Mid-infrared optical frequency combs at 2.5 based on crystalline microresonators, NAT Communications, Nature's Communications is the link. www.nature.com. Take a look there and you'll find it. So the keyword chalcogenide fibers will be in the next video. That was a keyword I found in the data. So I googled it to see what it was because it was interesting and I wanted to see what it does. Okay? Thanks for watching. Oops.